We said that in case of shaped beam and contoured coverage, we need the beamforming networks. What are they? They are some sort of microwave networks composed of transmission lines, usually waveguide at microwave frequencies and dealing with high powers, and power dividers, components that divide the power, the RF power in an equal way among an input port and several output ports. So the end result is a network that can feed an array of illuminators, these little horns that would illuminate a larger aperture, and they split the input signal with different, in different signals with weighted amplitudes and weighted phases, and the end result is this combination of the individual spot beams that would have been generated by the individual feeds into one single but well-shaped beam that fits at best my coverage area. Now we have already introduced the idea of reflectors, and we know that often reflectors are also called parabolic antenna or paraboloids. And it's important to remember one thing, and when we spoke about electromagnetic spectrum and electromagnetic waves, we explained that there is no difference, no basic difference between microwaves and optical frequencies. They are the same thing, only different frequencies of the same phenomenon. And the same applies also to antennas. It's not that the solutions that we invented for microwave application, for satellite application, are that different from the solutions we applied for optical frequencies. And this is so much true that we'll see many configurations of antennas are in fact the same configurations that were used and are still used today to make telescopes, optical telescopes. And here in this slide there is an example of a parabolic reflector used to concentrate the power from the sun. These are, so you can imagine the sun rays hitting the reflectors and then being concentrated, and to do what? In this specific case, to do something that is very famous. Every 4 years, you know that there is this torch that is ignited at Olympia in Greece, and then it goes and reaches the place where the Olympic Games will be performed, and the ignition of the torch is done through the sun of Olympia, through a parabolic reflector. So parabolic reflectors are in fact a very effective way to concentrate, amplify, let's say, the electromagnetic waves, whether they are in the optical field or in the microwave field. I wanted to show this slide to explain this concept very visibly. Parabolic reflector antennas. What are they? What is a paraboloid? Paraboloid is a surface generated by a parabola revolving around its axis. So we know what a parabola is, and we can imagine a solid that is obtained by rotating a parabola around the axis, and we get exactly a paraboloid. The paraboloids are the surface mostly used to realize antennas. All the antennas that we have, for instance, on ground at our homes to receive satellite TV channels are mathematically obtained through the rotation of a paraboloid. What is the mathematical characteristic of a paraboloid or parabolic reflector? They are linked to the geometric properties of the paraboloidal shape. Any incoming ray that reach the antenna, so you have to think of the famous plane waves that have been generated by another antenna far away. Of course, we are thinking now in reception. We said by the reciprocity principle that we can reason in terms of receive antenna or transmit antenna indifferently. So let's think of a receive antenna just for simplicity. So imagine we have a plane wave generated by somewhere by another transmitter, by another antenna. This plane wave, we can think of rays that reach the antenna and being reflected. all the let's say the laws of the geometric optics apply exactly to electromagnetic waves. There is no difference at all between the microwave frequencies and the optical frequencies from this point of view. As a matter of fact, many tools for the analysis of antennas are really called geometric optics tools, because the representation and the analytical approach is really based on the laws of optics. So in this case we have these rays that are parallel rays reaching the reflector, and because of the mathematics of geometry of the reflector, they are all reflected and concentrated in the same point, and this point is just the focus of the parabola generating the paraboloid. So you see that we have obtained what we wanted. We are now concentrating the energy from the plane wave in the same point. At this point we can put our illuminator, in this case it will be a receiving feed, and from that receiving feed then we can make interface towards our, for instance, receiver on board the satellite or on ground. So this is the basic principle. This basic principle is the same, for instance, used in a Newtonian type of telescope. Newtonian telescopes, let's say in the various forms, are based on a parabolic type of mirrors. In the case of optics, the mirror is reflecting optical waves. In this case, the mirror is reflecting microwave waves. The paraboloid itself is perfectly metallic, as perfect as possible metallic surface. All the laws of optics, again, apply in full. So, in the following slide, we see several configurations based on parabolic antennas. In fact, some of these configurations were invented for optical applications, and some of the telescopes that are used today and also in the past are in fact based on configurations that are here shown. So the simplest parabolic antenna configuration is the one shown on the left upper side of the slide, is the so-called axial or front feed or front fed type of antennas. You have your parabolic reflector as in the configuration as shown before, and then you have a horn, let's say a feed, that is the receiving feed that is put in the focus of the configuration. All rays are reflected by the reflecting surface, by the parabolic surface, and concentrated into the feed antenna. With, of course, what it counts is the area of the parabolic reflector, so the effective aperture of the antenna will depend on the size of the parabolic reflector. That is the one that we will use to calculate directivity. On the right side, upper right side, we have the so-called off-axis or offset feed or offset fed configuration. In this case, for several reasons why, we put still the feed in the focus, but not in the focus of the section of the parabola shown in the picture. In fact, what is shown in the picture is a part of a larger parabola. We use only part of it, so the focus is the one corresponding to a larger parabola. We use only part of it in such a way that the feed is not obstructing the reflector. And this is due to the simple fact that in the axial or front-fed configuration, feed being in front of the reflector is in fact creating some problems in terms of losses. The feed itself would somehow shadow the antenna. With the offset configuration, the feed is removed from the view of the reflector, so it helps from the point of view of losses. It also helps in terms of realization. We'll see that many times the antenna configurations on board the satellite are chosen depending on the mechanical constraints you have. You have to accommodate this antenna on the spacecraft, and depending on the dimension of the antenna and the configuration of the spacecraft, you might find one solution or the other. So there is always a compromise in terms of mechanical constraints, accommodation constraints, and of course also electrical or radiated performance and constraints. At the bottom of the picture we see another configuration that is used very much, is the so-called Cassegrain configuration. In this case, we put the feed, this is a particular type of Cassegrain, is a center axial fed Cassegrain. The feed is put on the main reflector in the focal plane of the reflector, but the rays are not hitting the feed directly, they could not, because the focus, it will not be in the focus, but rather they are reflected by a secondary reflector that is of convex shape, and this one is now concentrating the rays towards the feed. So it's a double reflector configuration. In fact, you can see it as a normal parabolic reflector antenna, axial fed reflector antenna, where the focal point is much farther away from the antenna. The use of a secondary reflector helps shrinking the overall dimension. Similar configuration is the one at the bottom on the right, so-called the Gregorian configuration, that is different from the previous one because of the type of the shape of the secondary reflector, which is concave instead of convex as in the previous case, but the approach is similar. It's a double reflector configuration. It's very compact because we can put the feed closer to the main reflector. In some cases it's in the center of it, but it can be also offset. We'll see some configurations where the feed is offset as compared to the main reflector, but the use of a secondary reflector helps again shrinking somehow the dimension of the antenna, the linear dimension of the antenna. So these are the basic configurations that are used. Let's look at them in some more detail. The front-fed reflector is very common. There are many ground antennas that are using this configuration, and we see also many type of satellite-borne antennas that are center-fed. You see here the problem of the feed, but also the problem of the supporting struts that are keeping the feed in the center of the reflector. Those are somehow shadowing, so there is a little loss associated with the shadowing of the feed and of supporting arms, the so-called struts, that are in front of the reflector. This is the front fed. The next one is the offset fed reflector antenna. This one is the most familiar because all, I would say, antennas used at home for receiving TV channels from satellite are in fact of the offset type. The offset configuration again has several advantages, apart from not creating shadowing of the main reflector, as you can see from the slide. There are other advantages also related to the antenna noise temperature, the fact that with the offset configuration you get less noise, for instance, from ground. The feed is not looking at the ground surface, so it doesn't get noise from ground. So there are several advantages related to this configuration. And now an example of onset and offset Cassegrain configuration. We have a picture. The photo refers to a non-set or axial fed Cassegrain configuration. The drawing on the right instead is an offset type of configuration. And we see the principle again is that you have a sort of virtual focus that is far away from the main reflector. The real focus, the physical focus, through the secondary reflector is put much closer to the antenna, so it allows a realization that is quite compact. You see that the double reflector configuration is equivalent, in fact, to a reflector, a normal axial fed reflector with a feed that is far away from it. And again, this has got several advantages in terms of radiating performance. And last, the Gregorian configuration, again, both in onset and offset. So the principle is similar. The subreflector, as compared to the previous case, is an elliptic type of subreflector, but the effect is more or less the same. We have with different characteristics, so every time we have to consider advantages and disadvantages also in terms of radiating performance, but the end result is to have a very compact type of configuration, both in the axial fed and in the offset fed approach, and so in several type of applications this type of antenna is better suited than the normal configuration with a single reflector. There are also antennas where we do not have reflectors. So the reflector antennas, a parabolic reflector, are a very effective way to get a very large aperture with a simple feeding element that is this feed that could be, we'll see some pictures of them, it could be a horn, so rather simple square or circular horn, rather simple elements that are illuminating a mirror, this parabolic reflector, so we get a large aperture, but on the transmit or receive side we have a very simple feed involved. In some cases we do not need any mirror, let's say any reflector, but we radiate directly from an array of elements. This is the principle of the phased array antennas. In the case of a reflector antenna, we orient the mirror, the parabolic reflector, to get the pattern and go in the direction of the pattern or the directivity going where we want to get, for instance, the wanted contour over the Earth. In the case of phased array antenna, we use a different approach. We have an array of individual elements. They can be of different type. They can be an array of waveguide feeds, horns, rectangular or circular, or can be, for instance, patches, microstrip patches antenna. We'll see some examples later. And I do not move the array of elements. In this case, in this slide, we see a linear array for simplicity, but you have to think also of a two-dimensional array. We move the beam generated by this array of elements by weighting the phase of the signal feeding the individual elements. So we have the same RF signal at the input of a beamforming network again. Beamforming network being, first of all, a divider, a network that divides the input signal among the different feeds, and then through proper components we weight the phase, we change the phase, and this change of the phase is such to change the orientation of the plane wave that is generated by the linear array. So we can orient this plane wave in such a way to get the beam oriented in the wanted direction. Array of antennas are used. They are called also direct radiating array, just because the radiation comes from directly from the feeds without the use of any mirror or reflector surface. And the gain in this case has to be calculated. I mean, it's rather obvious also to think that we are sort of sampling the area of the array through the elements. So it's rather obvious to think that the overall gain of the phased array is somehow the sum of the individual gains of the elements multiplied by the number of elements themselves. And this is exactly true under certain conditions. So in terms of dBs or dBis of the gain, overall gain of a phased array, it is given by the gain of or directivity of a single element plus in the number in dBs equivalent to the total number of elements. So in a phased array antenna and direct radiating antenna, we are sort of sampling the aperture, think of it in 2 dimensions, with a certain number of individual elements. So it is rather obvious to think of the overall directivity of the antenna as the sum of the individual elements. This is surely true under certain conditions. So the resulting formula for the gain of the direct radiating phased array antenna is gain of the phased array in dBi compared to the isotropic antenna equal to the gain of the individual element, the single element in dBi, plus 10 times the logarithm base 10 of n being the total number of elements. So this is a simple formula to derive the gain of a phased array. Of course, there are several other considerations to be done, but this is a first approximation of the gain of an array antenna. Examples of direct radiating arrays, in fact, as a matter of fact, this example is an active antenna, but is also a good example of direct radiating antenna. The two antennas of the Globasat satellites, Globasat first generation, were satellites made in the end of the 90s to create a constellation of satellites around the orbit. They are still operating. There is now a second generation that has been launched, and the constellation keeps working, operating at S and L band. And what is shown here are the two array antennas, one operating at L band and the other operating at S band. It's a good example of, you see the aperture made of a number of microstrip radiators that are all fed properly to create the beams and to generate a certain coverage over the Earth. And another example of direct radiating, if you want, phased array, is the antenna, navigation antenna of the Galileo satellite. This is now a transmit antenna but not active, so all the elements are put in a proper way. You see that the array is not completely symmetrical. I mean, there is a symmetry, but it is not that obvious. And there is a beamforming network, a passive beamforming network feeding properly the individual elements, and then the input of the beamforming network is attached to the power amplifier, the RF power amplifier, let's say, where the signal is fed into the antenna. So these are examples of direct radiating arrays, so antennas on board satellites not using a reflector to generate a large aperture, but radiating directly from an aperture composed of individual elements. So if you want an aperture sampled by individual elements that are approximating a part of the aperture itself. We said that some direct radiating antennas, in fact also some reflector antennas, are active antennas. We introduced the concept of active antennas when speaking of the reciprocity principle. We said that the reciprocity of antennas applies when you have the antennas made of reciprocal components, not including, for instance, active components such as low noise amplifiers or power amplifiers. Here shown in this slide, on the left side, are two examples of receiving active antennas. The transmit antennas would be similar, but only instead of low noise amplifiers, we would have RF power amplifiers, either solid state or TWTAs. The top one is still using a reflector, so there is an array active because the individual elements are attached to low noise amplifiers. Then the low noise amplifiers feed a beamforming network, which can be analog or digital. These are very sophisticated techniques that are presently used on board satellites. Or it can be instead a direct radiating. In case of direct radiating, you do not have a reflector, you just sample your complete aperture with a certain number, even a high number can be, of individual elements, again attached to the active components, in this case being a receiving antenna, low noise amplifiers, or otherwise RF power amplifiers. On the right side of the slide, there is an example of active array antenna. Is the active antenna of the Cosmos SkyMed satellite, which is, as a matter of fact, is a radar antenna. So it's an active antenna where the elements that are printed microstrip patches are connected to both low noise amplifiers and RF power amplifiers through a switch. So the antenna works in transmission and then receives the reflected waves from ground, like in any radar. And it is a good example of active, rather complex and sophisticated active antenna with direct radiating into space. And this ends the second lesson of my introduction to spaceborne antennas.